This activity focuses on the periodic table. The periodic table is an arrangement of all of the known elements, and this is in such a way that infers a lot of different things. This experiment focuses on using and utilizing the periodic table. The periodic table is a listing of all of the known elements. You have pre-transition, transition, post-transition, and rare earth elements all combined in a single table. The activity looks at the different values that are associated with the individual elements, as well as other trends that you can find on the periodic table itself. The periodic table displays the elements in a way where you can easily identify the different properties and trends within the table, as well as the different components of the individual elements. Elements themselves are specific, where atoms are more general. An element is a unique atom. Atoms themselves are basically the foundation of chemistry. Absolutely everything is made up of different atoms. So while one atom can exist by itself, all different types of molecules as well as other physical things are made up of all of these atoms. One molecule of ethanol contains 9 different atoms, while one molecule of the protein insulin contains 788 different atoms. Atoms themselves have 3 components within them. Protons, neutrons, and electrons. The protons are found in the nucleus, or the center of the atom, and these have a positive charge associated with it. The number of protons is what dictates the element. Elements themselves have a unique number of protons. Any atom with a proton, with only 1 proton, is hydrogen. Any atom with 2 protons is helium. So by changing the number of protons, you're changing the element itself. Neutrons are also found in the nucleus of an atom, and these have a neutral charge. And when you change the number of neutrons, as long as the number of protons is constant, so it's the same element, the number of neutrons can vary. So in the case of carbon, carbon has 6 protons and usually 6 neutrons as well, but it can also exist with 7 neutrons or even 8 neutrons, all still being carbon, but a little different. These elements, or these different number of neutrons in elements, are called isotopes, and these will be touched on a little bit later. The last component of an atom is the electrons, and these are found outside of the nucleus, where the protons and neutrons are condensed in the center. The electrons are surrounding that nucleus. Electrons themselves are negatively charged, so they balance with the protons. In a neutral atom, straight from the neutral element straight from the periodic table, the number of protons and electrons are the same. However, electrons can move around. This is where the actual chemistry happens, is moving electrons between different atoms. That's how chemical reactions take place. And an atom can exist that has one extra electron. Overall, if it was neutral and you added one negatively charged electron, the whole charge would be negative. Likewise, you could also take an electron away, and now there would be too few electrons to balance out with the positive protons, and the overall atom would have a positive charge. These elements with differing numbers of electrons are called ions, and those will also be touched on in a little bit. So on the periodic table, it's arranged in such a way that you can see properties, and the most basic values from the periodic table exist in almost all of them. While many periodic tables can list other numerical values or properties, pretty much every single one would have these three components: the atomic symbol, the atomic number, and the atomic mass. The atomic symbol is just the abbreviation for the element, a 1 or 2 letter abbreviation. If it's 1 letter, it will always be the capital letter. If it's 2 letters, the first letter is capitalized and the second letter is lowercase. It must be lowercase because some of these elements have only 1 letter abbreviations, and if you 2-lettered abbreviation has them both capitalized, it could be mistaken for 2 separate elements. You'll notice when you go through the periodic table that not all of the atomic symbols make sense. Having letters and things that don't even appear in the name of the compound. This is because some of them are using the symbol based on a previous name, either in a different language or Latin or something that used to be more common in use but no longer is. The atomic number is the numbering scale for the periodic table: 1, 2, 3, 4, 5. So as I had mentioned, anything or any element with a number of protons as 1 is hydrogen. This is the atomic number of hydrogen. The atomic number of helium is 2 and has 2 protons. So as the periodic table takes shape, the atomic number is continually increasing, and that dictates how many protons and electrons are found in the element itself. The last value typically on a periodic table is the atomic mass, or the average atomic mass. This is the number in grams that is used, or that is needed, to make up 1 mole of atoms. And 1 mole is just 6.022 times 10 to the 23rd. That is, a mole is the name of a number. Just like 1 dozen is 12, 1 mole is 6.022 times 10 to the 23rd. Atoms and elements are so small that you need to include a lot of them when working in the real world. There are a lot of elements, there are a lot of atoms that are contained in 1 gram of anything. And chemistry occurs using this unit, the unit of a mole. So here is the periodic table itself. It's shaped in a way where the different elements are grouped in different sections. The columns are referred to as element groups, while the rows are referred to as periods. The elements listed in an atomic group usually have similar characteristics. So the different groupings are in this middle area that has kind of separation between the left and right is the transition metals, very appropriately named. Before the transition metals on the left-hand side are the pre-transition elements, the post-transition elements after the transition elements, and rare earth elements. Now, in these pre-transition elements, the individual groups have specific names. So the first group is the alkali metals, and the second group is the alkaline earth metals. These are all metallic elements and are typically pretty reactive. The alkali metals are extremely reactive, even exploding if you drop them in water. The alkaline earth metals are more tame, but still can be moderately reactive. The transition metals are in the center of the periodic table, and they have some different properties, different unique properties. They're very conductive, they're typically rather dense, and these types of atoms, these transition elements, can have multiple different versions of their ions or varying numbers of electrons. The rare earth elements are usually shown below the periodic table. However, in many older versions of the periodic table, you will see it stretched out. These two rows actually appear right here in between the pre-transition elements and the transition elements. However, that extends the periodic table to be very, very long. So most times they're typically shown as a subset or underneath the rest of the periodic table. The top row is referred to as the lanthanides, just because in reference to the fact that the first element is lanthanum, and the bottom row is referred to as the actinides, again, because the first element in that row is actinium. Now, a lot of these elements in the rare earth elements are radioactive, and many of them are even man-made. Uranium, element number 92, is the heaviest naturally occurring element that's currently known. All of these other elements past uranium, all of these heavier elements, are man-made. They're synthesized through nuclear chemistry by combining protons to create new elements. The post-transition elements occur on the right-hand side of the transition metals. And these elements are both metal and non-metal. The transition between them is this stepwise line cutting this block in half. The lower left are all metallic elements, and the upper right are all non-metal elements. Those that kind of straddle this line are many times referred to as metalloids. They can have properties similar to either a metal or a non-metal. Group 18, this very last group, is many times referred to as the noble gases. They are all, at room temperature, they are all in the gas state, and they are very, very non-reactive. They are perfectly happy as they are and very incredibly stable. So they've always kind of been referred to as the noble gases. Group 17 is also referred to as the halogens. These are things, fluorine, chlorine, bromine, and they would make things like chloride for sodium chloride, fluoride that's in tap water or that the dentist will put on your teeth. And they have, again, each group has a set of properties that are kind of unique for these individual groupings. As mentioned previously, you can have an element with varying numbers of neutrons, and these are referred to as isotopes. And these are where the atomic mass comes from. So each proton and neutron weighs approximately the same amount. They each weigh 1.67 times 10 to the negative 27th kilograms. They're very, very light. And this amount is approximately equal to, if you multiply this by Avogadro's number for 1 mole, this is approximately equal to 1 gram. So it would take 1 gram to contain 1 mole of either protons or neutrons. So these are referred to as AMU, atomic mass units. And this is the unit that's in the atomic mass on the periodic table. So in the case of carbon, carbon has 3 different isotopes. Carbon 12, which has 6 protons and 6 neutrons. 6 plus 6 is 12. And it's an abundance of 98.93%. So the amount of carbon present is 98.93% all this kind. There is a trace amount of carbon 13. This has 6 protons and 7 neutrons. So a total mass of 13 atomic mass units. And this only has an abundance of a little over 1%, 1.07%. The last isotope of carbon that can exist is carbon 14 with 6 protons and 8 neutrons with an atomic mass of 14. This one, however, has an abundance of 0. This is because carbon 14 is radioactive, and if ever it exists, it breaks down and reverts back to one of the others. To calculate an average atomic mass, you need the atomic mass of the individual isotope and its relative abundance. So you're taking these and multiplying them together and adding them up. In the case of carbon 12, it weighs 12 atomic mass units, and 98.93% of all carbon is carbon 12. So you multiply 12 by 98.93%. Carbon 13 has an abundance of 1.07%. So you multiply those together as well. And then you add them up. And this will give you 12 0.0107 AMU. This is the average atomic weight of carbon. This method can be used for any element. You need to have all of the isotopes combined to figure out what is on average the weight that it takes, or the mass that it takes, to equal 1 mole of atoms. The last point I'm going to touch on is ions. So while isotopes are elements with varying numbers of neutrons, an ion is an element with varying numbers of electrons. So whenever an element undergoes a reaction, typically it's always with the electrons. Nuclear chemistry refers to the nucleus, and that's where the chemistry happens, but all other chemistry occurs with the electrons, moving back and forth or being shared between different elements. And sometimes even completely leaving or completely attaching to a different element, creating these ions. A cation is an element that loses an electron, so it lost a negative charge. Therefore, that element now overall has a positive charge. And anion is the exact opposite. It's an element that gains an extra electron, so you're adding a negative charge, and therefore the entire element becomes negative. The properties between the atoms and their elements are extremely different. Sodium is an alkali metal. It is very reactive and explodes when it touches water. Sodium ion though, is very non-reactive. That's the primary component in sodium chloride, or table salt, that we eat and our body needs to survive. But when we put salt on our food, it does not explode. While they are the same element, the difference of this one electron really makes the properties incredibly different. This experiment uses an online interactive periodic table that you can use to look up a number of properties and values for the different elements. So the website is ptable.com, and you're going through and looking to see which elements have different properties, what are the properties of these elements, as well as looking at different isotopes, different ions, and just overall the structure and formation of the periodic table. When you first go to the periodic table simulation, it will be in this format. You're looking at the periodic table, looking at these different element groups, and you can see where they are on the periodic table and what their names are. In the first part of the experiment, or in the first part of the report, what you're going to do is go through each one of these element groups and select any of the elements, any one element from each group, and you're going to record the atomic name, the element name, the atomic symbol, the atomic number, and the atomic mass. Keeping in mind that when you're recording an atomic mass, it should always have the units of grams per mole. This is how many grams 1 mole of the atom or of the element would weigh. In this case with nitrogen, nitrogen weighs 14.007 grams per mole. That is, it takes 14.007 grams of nitrogen to contain 1 mole of atoms. A large section of the report looks at the different properties of these elements. Initially, when you first log into this periodic table, you can see that they are separated either as solid, liquid, gas, and based on the temperature, which you can change either through this slide bar or by changing the actual temperature itself, you can see how the physical states of these elements change as a function of temperature. The rest of the properties are all listed on this left-hand side. So you can go through and select any one of these elements, and you can see that the properties along the side are changing with the element. And what you're going to do is, in one section of this, you're going to choose one element and record a number of different properties for that one element. The other thing you're going to do is look at the different property trends on the periodic table. And how you can do that is on the left-hand side, select one of these properties. And what it does is it changes this periodic table to a color-coded system where you can visually see the different data trends based on the periodic table. So in the case of something like conductivity, you can see here that silver and copper have the highest conductivity and the elements on the outside have the lowest. Specific heat, hydrogen has the highest and it gets lower as you move down. You're going to be going through and looking at the melting point, boiling point, electronegativity, electron affinity, and the atomic radius and density for all of these different elements, or at least looking at the overall trend as they appear on the periodic table. What is the highest melting point element? What is the lowest melting point element? And what are those values? Being sure whenever you record a value, you're also recording the appropriate unit. Also on this periodic table, there are other tabs up top, and you're going to work with a couple of these. Under the Isotopes tab, you can go in and select any one of these elements, and it will bring out all of the different isotopes of that element available. And in the lab report itself, what you're going to do is look for a few of these different elements and look at their stable isotopes. The stable isotopes right here, are highlighted in black. So you can see this one here has one for boron, or I'm sorry, for beryllium has one stable isotope. And you're going to choose a couple of different elements that each have at least 2 stable isotopes. This interactive periodic table does give you a number of different isotopes, but they're not all stable. You're only looking for what are these stable isotopes, and you're going to record. So what you'll be doing is recording the element, the average atomic mass, and then for each of the stable isotopes, you're going to record how many protons there are in this isotope and how many neutrons there are, as well as the percent abundance of that particular isotope. So when you're going through, you're going to choose at least these elements that have at least 2 stable isotopes. So you might have to look around for a couple of different stable isotopes, and you should be recording all of them. Some of them will have more stable isotopes than others, so you can look around and see which ones you would like to choose for the lab report itself. The last part of the periodic table report is under this Compounds tab. And when you go to this Compound tab, what this does is show you all of the different compounds, or at least a number of the different compounds that can be created using the different elements on the periodic table. So in this section, you're going to create a few different combinations to see what compounds are created. You're going to take one metal and drag that to the area, and then two non-metals and drag that as well. And on the left-hand side, it shows you compounds that contain these three elements. So what you're going to do is simply go over to the side and choose any one of these elements, or I'm sorry, any one of these compounds that contain the one metal and two nonmetals. And you're going to record the chemical formula as well as the chemical name. And this is a great tool when looking around to see what different compounds can be created using these different elements. This website can be a very good tool for you to use to look at the different elements, to look at the periodic table itself, looking at the different properties of these elements, looking at their isotopes, the different compounds they form, and even looking at the electron configurations and orbital diagrams of these different elements, and looking at the different orbitals as well. So again, in the first part, you're recording the name, atomic symbol, atomic number, and atomic mass for a number of elements in each element group. You're looking at different properties, melting point, electronegativity, density, and radius, and seeing which elements have the largest and smallest of those. Choosing any element and recording its melting point, boiling point, electronegativity, electron affinity, ionization energy, radius, density, abundance, and the year discovered. In the Isotopes tab, you're choosing three different elements and recording its name, average atomic mass, and for each isotope, recording its atomic mass and the number of protons, number of neutrons, and its percent abundance. Lastly, in the Compounds tab, you're selecting one metal and two nonmetals and recording the name of any of those compounds that come up, as well as their molecular formula. In the end, this activity is all about using the periodic table. You're using the table to figure out atomic name, atomic number, and atomic mass of these different elements, the names of the different portions of the periodic table, as well as other properties that the periodic table can show you. Hopefully, you can use the periodic table both in the activity and in lecture books and in other areas to determine these properties and use them throughout chemistry.